compression, the effect of axisymmetric imperfections. And once again, you see that you have different curves depending on whether you have or not stiffeners and whether they are on the outside or on the inside. Same thing for externally pressured. Now, the interesting here is, we'll come back. This is lightly stiffened, okay? The one with isotropic external pressure, then lightly stiffened rings on the inside or on the outside. And if you notice, he says light stiffener, the ratio AR-DR times T is 0.2. The one EIR-DR is 10. That is what he calls light. And you get essentially asymmetric buckling modes. One of the restrictions for the B factor to exist at the buckling mode must be asymmetric, single-valued and asymmetric. Now, you see this one now here, and essentially what has happened here, he has once again light, but this light is considerably stiffer than the previous one, because the previous one, AR dr over T was 0.2, this is 0.5, this here was 10, this is 20, and I don't remember what the eccentricity was. Let me look. The eccentricity was plus and minus 2, and he increased the eccentricity. And essentially what happens, that for this combination of stiffeners, depending on the length of the shell, you get these buckling loads as straight lines, and essentially corresponding to those buckling loads, you have a rings as an axisymmetric buckling mode. Okay, and if you have axisymmetric buckling mode, buckling mode, you don't have a B factor, you still can look at imperfection sensitivity if you use axisymmetric imperfections. Okay, now, the last question that you always get asked if you present this type of, do these type of presentations, I said level 1, level 2, level 3, right? Level 1 is very approximate, level 2 is more accurate, level 3 is where you have your finite element or two-dimensional finite difference code. That's the most accurate one. And I have presented you results that on this plot occur here in the neighborhood. So let us see what this plot is. This plot was produced with STEGS A, so it is produced with a level 3 code. It was done for a stringer stiffened shell, and boundary conditions are SS3, simple support 3, rigorously enforced. What do you see here? Here you have the load, which is normalized. Why did I pick 136.5 to normalize with? Because that is precisely the buckling load of this particular shell if it is perfect. It buckles with 11 waves in the circumferential direction at that load. So what I did, I always like rho to have, for perfect shell, the bifurcation at 1. No, I can get that by precisely dividing the buckling load, and then it bifurcates at 1. This is the pre-buckling path, which is axisymmetric. Here it bifurcates, and you get the asymmetric bifurcation. I can also push it further. I can push it more and more and more and more and more, and at some value, I will get axisymmetric collapse, right? So what it happens, it develops a bunch of ripples, axisymmetric, and then it collapses. Here is where we were talking about it, the simplified analysis. And notice that if you now have the capability, and my STEGS A has it, you can step over from the pre-buckling path onto the post-buckling path. And then you just follow down there. And this is actually calculated. It goes down, down, down. It turns around and comes up again. Now, Goyte's theory, the asymptotic theory, describes what is happening around there. And essentially what we do, we calculate the slope, the initial slope of the post-buckling path. And if the initial slope is negative, then we say the structure is imperfection sensitive. Remember that plot that I showed you where the post-buckling path was described, rho is equal to 1 plus b xi squared, where we had the parabola turned downward. Now, look, here is the beginning of the parabola, and just think of it continued on that side. So Coites' theory is essentially correct in that neighborhood. And you can then test it with this very advanced code, because what do I have here? Here I have a curve, not for a perfect shell, but an imperfect shell. What imperfection did I put in? I put in the buckling mode that I found there. How big did I put it in? At 1 wall thickness. And so what you get, it comes up, and then when it reaches about 60%, here is the limit point, and it goes then, and it kind of approaches that curve. We know that in the deep post-buckling region, imperfections have minor effect. You can also do this for C4 boundary condition, fully clamped, u, v, w, w, comma, x. And you can see how the shape of the curve changes. Essentially, and that's the interesting thing, it became apparently more imperfection sensitive, right? Right at the bifurcation point, you have a deeper slope, right? If you go back, here the slope is less. Now, this is a solution technique where you are not restricted to the immediate neighborhood. Coites' theory, any asymptotic theory, is restricted to small values of xi. And notice the interesting thing is, despite the fact that this one here initially predicts a much bigger imperfection sensitivity, when I input the buckling mode as an imperfection, 1 wall thickness, and I follow up the curve, it once again carries about 60%, right? So, and go back to the other one. Sorry, I went in the wrong direction, I guess. No, I lost it. What happened to the... Let me see. The wrong direction? Okay. It goes up to a certain point and then reverses.
It's more stability.
Okay, it goes that way. Okay. Okay, there it is. I have it. Okay, so this is 60%. Now, hopefully it goes one step further back. Yes. Okay, so here you also, if you look, it's about 60%. So not only is important what happens very close to the bifurcation point, that's the first indication. If you really want to reassure yourself, you actually should calculate further what the post-buckling path does.
But if the imperfection is much smaller, then you will get more.
Sure. I mean, Coites' theory is asymptotically correct. So it is exact for very, very small imperfections. 1 wall thickness in this case is too big, right? Okay, so I guess that is pretty much what I had to say today. And we'll be happy to answer some questions if you have.
Okay, I will start to ask questions. So there are, okay. First, you may want to repeat questions when I'm asking because I will record it. So what you are presenting actually is something which I wrote here, something like computerized library of knowledge and its developments throughout the years.
Yeah.
Now, do we need this development, or we just should take the best available thing?
Okay, so the question was, do we need a library of available knowledge, or do we take the best available thing? If you have the knowledge in your head, you don't necessarily have to acquire it by exercising through the different levels. I dare to say that people who try to do it the first time, and if they try to use the most advanced tools, they're probably going to be going in the wrong direction. Because computers don't replace thinking. If you just have the facility in your fingertip, I mean, you still have to input the things cleverly, and very general codes have very many possibilities with flags, right? You just change a flag and it does something else. So you have to be very careful. You have to have this advanced knowledge to which flag to activate and to look whether it is going in the right direction. You also have, in advanced codes, such flags which determine the accuracy of the solution. I mean, they usually want to go fast. So you have little flags which tell, do you want 3-digit accuracy, 4-digit accuracy, 5-digit accuracy? If you want to go faster, you choose 2-digit accuracy. Now, what you can get is what in terminology of numerical analysis is called, you can get onto spurious modes. Modes that in the reality don't exist. They only exist because you are only asking for 2-digit accuracy. If you repeat the same work with 3 or 4-digit accuracy, they won't appear. They don't exist. And you have to have advanced knowledge, what I have shown you before, level 1, level 2, because if you don't have it, you don't know when the thing is spurious and when it is real. If you model things right, the level 1, level 2 solution, level 3 solutions, there should be a continuous improvement, not jumps. You're talking about percent. Generally, you will get with a level 1 solution if you don't worry about boundary condition, if SS3 is okay. You get within 10% of the final result. So it is, I think, very important to acquire knowledge and then to go to the powerful tool.
Because, for example, you showed that Hutchinson Frauenthal model is better than Hutchinson-Amazigo model. So at least between these two, you may want to leave only the one which is better.
Okay, the question